Good morning, good afternoon, good evening, and welcome to a post on quantum computing. It's called Dreams of Quantum Computing. I don't come from this field, but I find that sometimes having an outsider's perspective from another branch of physics can help shed some light on issues that seem mysterious to people who have their heads buried in the sands of abstraction. People have been making transistors, the building blocks of computer chips, smaller and smaller ever since the day they were invented, and we are already sort of hitting the limit of how small they can be. To continue making computer chips faster would require a completely different concept, and today billions of dollars are being invested in quantum computing research. In the blog linked below, there are a couple of very nice videos that give a good introduction to the topic. For example, you see a system where a long wavelength flips the nucleus of an atom, and a short wavelength flips the electron of the atom. And they believe that they can put a bunch of these all together and make a quantum computer out of it. So I am not entirely sure that I can understand how you can put more than one of these atomic systems in a grid, but I hope I can figure that out by the end of this article. What is easy to see from the field of quantum computing is that headlines are made when Google announces that they have used a quantum computer to perform a complex calculation faster than ever before possible. But how much of this is hype and how much is real? Because in science today, it's often very hard to tell. The quantum computer completed the complex computation in 200 seconds. That same calculation would take even the most powerful supercomputers approximately 10,000 years to finish. The team of researchers led by John Martinez, an experimental physicist at the University of California, Santa Barbara, wrote in their study published Wednesday, October 23rd in the journal Nature. So I read this and I think, what? If there isn't another computer that can check that the calculation is correct, how can you claim that your computer has performed a correct calculation? The article continues and says that the calculation that Google chose to conquer is the quantum equivalent of generating a very long list of random numbers and checking their values 1,000,000 times over. The result is a solution not particularly useful outside of the world of quantum mechanics, but it has big implications for the processing power of a device. I mean, if that doesn't make sense to you, you're thinking. If it makes perfect sense to you, there's a good chance that you're not thinking. The calculation was impossible to verify, and it is not useful for anything, but they claim that it implies that the device has processing power for practical calculations which have not been demonstrated. Okay, I'll maintain my skepticism about that last non-demonstrated claim. What I know is that quantum mechanics calculations are ideally done with infinite matrices and infinite determinants, but under practical conditions for quantum computing, finite matrices for two-dimensional systems are used, and there is therefore a lot of extra uncertainty associated with each calculation done by a quantum computer. There are some really big open questions about whether or not any of this is ever going to be useful. In fact, I become quite concerned when I read that top experts in quantum computing write that the greatest potential for quantum computing is in simulating quantum systems. Simulating or replicating? The language used to market quantum computers is too fuzzy for my taste. And given what I know about fuzzy logic and Bayesian analysis on a network, I have a lot of doubts about error propagation. When I think of a physical system that mostly closely resembles a rudimentary quantum computer, I think of a thin film of metal grains which have been randomly scattered across the surface of a piece of glass. When that network of metal grains is at the percolation threshold, the surface is half dielectric and half metal. If light passes through that film, it will often be absorbed by the system, and a random assortment of magnetic hotspots will occur across the film. If the frequency of the light changes, the distribution of hotspots changes. The hotspots are like qubits, and one can solve for the local field intensity for a given distribution of metal grains and a given frequency of light. But you can't program them to be anything other than what they are. To transform such a system into a quantum computer, you would need to construct a grid of metal grains that can reorder themselves on command, and that reordering would be a slow mechanical process. This would not be a fast computer, but rather a simple encryption device, and I'd be surprised if such technology had not already been in use since the 1990s. This is based on, I did an undergraduate thesis on the local fields of metal dielectric thin films, and that sort of application seemed kind of obvious. And that was back in the 90s. If you understood that paragraph, and if you connect it to a picture of a phosphorus atom used to modify the pattern of hotspots on a metal dielectric grid, welcome to the moment you realize that physicists are not actually smarter than you are. They've just been psyching you out. If you did not understand that last paragraph, read on and I hope it becomes clear. It helps to first understand what the building blocks of all quantum computers really are. They call these building blocks qubits, but the word means something different depending on who you are talking to. So you have to be a bit careful. Most fundamentally, a qubit is just a swirl of charge or space or time, depending on the convention you choose. For example, consider that the difference between an up qubit and a down qubit is very much the same thing as the difference between electrons and positrons, the difference between matter and antimatter, the difference between two electrons going in opposite directions in space, the difference between two electrons going in opposite directions in time, the difference between a spin-up electron and a spin-down electron, the difference between a positive hole and a negative hole in a semiconductor, the difference between an electron with weak isospin and an electron without weak isospin, the difference between a positive energy particle and a negative energy particle in a Dirac sea, the difference between clockwise swirls of charge and counterclockwise swirls of charge, the difference between an electric monopole and a magnetic monopole. So basically, a qubit is whatever a user wants it to be. It's a fantasy onto which we project all of our science fiction hopes and dreams. In the next section of this post, I will break up these hopes and dreams into mathematical, physical, computational, and personal categories. So, mathematically, a qubit is an abstract object which is literally in a mixture of up and down states. A grid of qubits can be represented by a matrix, and if you change one qubit in the matrix, all of the others flip in a predictable way. By flipping individual qubits, you can create as many different patterns as there are qubits in the matrix. I think of this as pushing a single key on a piano and a whole song comes out. Each key produces a different song, and if you push the same key several times, there will be some variation in the song that comes out. So, from a mathematical perspective, a quantum computer seems promising. But physically, a qubit is a whirl of space which is under the influence of the noisy environment. An up qubit is clockwise spinning space, and it enjoys being surrounded by down qubits, or counterclockwise spinning space, and vice versa. Left in isolation, the qubits organize themselves such that they are happiest. But if one qubit is disturbed, the whole grid may rearrange itself. If some of the qubits are confused about how to arrange themselves, they will be in an undefined state until they are measured, and the outcome of the measurement will be unpredictable. The tricky thing is that if you measure any single qubit, you disturb it along with every other qubit on the grid. So while you may be able to play a song by pressing a single key on your quantum computer piano, you can't hear the song unless you find a way to measure all of the qubits at the same time. If there is any synchronization problem, you will not ever get a song out that has any measure of repeatability. It will be completely random. And I feel somewhat qualified to comment on this after having done femtosecond synchronization experiments in my PhD. Computationally, a qubit, so that is just the physical aspect. And then you have computer scientists. They're a different community, and they have their own idea of what a quantum computer is. So what I'm trying to show is that each different subset of the community has a different idea of what this object is, and those ideas are not terribly consistent. And when you have that kind of miscommunication, you can get a group working really hard on something, and they say, see, we finished the job, and then the other group says, oh, but wait, you were supposed to do this. And they say, what? So, got to be careful here. So, computationally, a qubit is neither a 1 nor a 0, like a typical bit. And this is the reason why one can build a system in which flipping one qubit will instantaneously flip a bunch of other qubits. In a typical computer chip, there will always be a delay from sequential processes, but in a system of qubits, instantaneous action in parallel is possible. A grid of qubits could potentially be used as an encryption key, something that has to be carefully preserved and which can only be read out very carefully. What? Personally, I think an encryption key which has the tendency to self-destruct sounds like a very bad idea. You have to preserve it in a super-cooled cryo environment without any noise disturbing the system. Ugh. Entropy is something that I haven't heard mentioned in any of these descriptions, as well as the problem of isolating a 2D grid from a 3D environment. There is also some concern about how much speed one really gains in such a system, because the spin flip can only occur as quickly as the duration of the light wave or pulse used to read or write to the qubit. And I mean, right now we can make 800 nanometer lasers and control them quite well. You can even make 270 nanometers by tripling the frequency. But getting shorter wavelengths requires extremely expensive machines, and controlling those machines is something we do not have under control yet. I mean, that's what accelerators that make free electron lasers do. The system just gets more complicated and harder to imagine. What's hard for me to understand or for me to feel good about is how did so many people get wrapped up in a concept that they all misunderstand in different ways? I personally blame quantum mechanics education. The first thing that one learns in quantum mechanics class is that there is a fundamental difference between classical probability and quantum probability, because classically, if you keep taking measurements of something, you will continually increase the accuracy. But in a quantum system, you could take an infinite number of measurements, but you can never increase the accuracy past a certain point. We are taught to say that this is an intrinsic uncertainty, a feature of nature and not a feature of our measurement tools. But in the sense of quantum computers, this is very narrow-minded, because the math of quantum mechanics is designed to calculate things with non-local common causes in, for example, an accelerated reference frame for which you do not know the initial conditions. In essence, the math of Hilbert space was invented to calculate how things behave when the world is shaking. It does this by shifting the perspective such that the shaking seemingly disappears from the calculation, manifesting itself as an uncertainty or orthogonality relationship between conjugate variables. A non-local common cause looks strange if you think of it as spooky action at a distance, as Einstein did. What makes quantum mechanics seem strange is that whereas there is a delay between when the light is produced in the sun and when it reaches us, there is sometimes no delay between two quantum occurrences which appear to be causally linked. Once again, this only seems mysterious if you don't picture both objects in a shaking reference frame. You have to think outside of the box that defines quantum mechanics in order to understand what happens within it. While we cannot access information about this shaking in order to predict what it will do next at a given point in space and time, that doesn't mean that there isn't a perspective that can. We are capable of imagining such an absolute perspective and approximating such a perspective, even if we are not capable of seeing directly through those eyes. To catch a glimpse, try looking at the most basic experiment in quantum entanglement with a new perspective. It's the one where you're seeing the difference between classical and quantum entanglement probability. Classical probability tells us that the entanglement statistics should follow one curve, while quantum entanglement statistics tell us that the result should follow a different pattern. And since the experiment matches the quantum story, there is more correlation than expected by classical mechanics. End of story. Or is it? What if you think of the shaking of the reference frame as an unmeasurable systematic error in the measurement, which causes the discrepancy between the classical and quantum results? The objects simply move together more often than they would if their motion was initiated by some random process. Thus, the objects share some externally caused common event in their history. I know that the day when people stop believing in things that they can't understand is a bad day. But at the same time, we shouldn't have too much faith in people who claim to understand mysteries that are incomprehensible, in a superposition of states defined by understanding everything perfectly and understanding nothing. This is relevant because if you don't think outside of the box that defines quantum mechanics is incomprehensible. And we have a whole population of people who have been trained in the shut up and calculate method of instruction where they're not supposed to understand it, they're only supposed to execute a recipe and to say, it works, so I understand it. No. If you want to think even further outside of the box, you might speculate that the brain is a quantum computer, in that a single synapse encodes multiple bits simultaneously, as in multitasking. That is actually an idea I could get on board with. There is something special about negative entropy, quasi-biological systems. And I think that there is a way to describe a living creature as a device powered by room temperature superconductivity. Although I do let myself get a bit lost in the deep end. Nevertheless, and my only salvation is when I return to fundamentals and just think about geometry. That's the only way to stay grounded. Nevertheless, the idea that quantum computing requires the many worlds interpretation of quantum mechanics, as has been popularized lately by Sean Carroll, a pop scientist, this is too far in the deep end for me, because it rests on the idea that for us to have free will, there has to exist another world in which we could have chosen otherwise, and that much of our thinking actually occurs in parallel worlds whenever a choice must be confronted. I've linked in the blog post below to the flaws that I see in that concept, an article I wrote on that, and also an article about consciousness and quantum mechanics. So, personally, I think that kids should be learning about real physics rather than imaginary quantum computers, neutron stars and black holes, and that they should spend more time studying spinning tops. And because the world can really, even quantum mechanics can be understood with a spinning top. You know, it's one of those systems where you can make it work, you can spin it, and you've made the system work, but you don't understand why it works. And then you study all of the angular momentum and everything, but when it comes down to it, there's a microstate that you can never access. You never can figure out what the microstate is at the tip of that spinning top. And those sort of unknown variables are critical to understand in terms of how they limit us. And I think that people who are building quantum mechanics have not yet understood their limitations. They're the sort of people who say, look, the machine works, but they don't understand how or why. And they don't understand what its limitations are, that it can't do all the things they think it might do. And because I am going to try to finish this series of videos with by ending each video with a song, I'm going to choose a love song for this post, and it's a love song about a machine, a love song about the machines that I was trained to love in my doctoral work. Accelerators. So, a love song for an accelerator. I bought you some Clystrons for Christmas, a damping ring, a Mach 7 Firetron, and everything. Love makes me treat you the way that I do. Gee, baby, ain't I good to you? Love makes me treat you the way that I do. Gee, baby, ain't I good to you? All physicists love the things they study, and that's where you've got to be careful.